Homework 3.2, Polynomial Functions, Video 4. Yes, it is Video 4. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. The following examples directly associate with questions 5, 6, and 7 and are also parts of questions 13 and 14. In the previous two videos, we discovered how to find the end behavior of the graph of a polynomial function by analyzing its leading term for its degree and its leading coefficient. In the next two videos, we're going to discuss finding x-intercepts. Now, if you're wondering about y-intercepts, yes, we will incorporate them when we get to some of these questions that tie everything together, but it's the same as it's always been, stick in 0, so it doesn't merit a whole video on its own. And we have found x-intercepts before, and the approach is still the same, but there's a little bit more to it than just finding the x-intercepts. For example, we're going to find the x-intercepts for the following functions' graphs, but we're also going to determine each intercept's multiplicity. I'll define that in a moment. And we're going to state whether the graph crosses the x-axis or touches the x-axis and turns at each x-intercept. Because the problem is not all x-intercepts are made the same. When you have a graph in x-intercepts, for example, let's say that the graph's going to have these x-intercepts. When you get to an x-intercept, you can actually do one of two things. Number one, which most people expect, is you cross over to the other side. But it's also possible when you reach an x-intercept to change direction and go back and basically turn around. So you don't really cross the x-axis, you touch it and turn around. And let's just cross this one. So it would be good information in advance of graphing to know where will a graph actually cross the x-axis and where will it actually touch the x-axis and turn around. That's really helpful when you're sketching a graph. And in case you haven't figured it, by the time we get to the end of this series of videos, we're going to be sketching some of these graphs. So how can we determine whether or not a graph will cross the x-axis or touch it and turn around at an x-intercept? Well, the answer lies in something called multiplicity. For our purposes, the definition of the word multiplicity would be the power of the factor that produced an intercept. So let's find some intercepts and some multiplicities, and then we'll talk about what it does. Of course, I've already got it right here. All right, so first off, how do you find x-intercepts? Well, remember that if you're an x-intercept, you are on the x-axis, which means your y-coordinate is 0. And in a function, the y is what comes out. So to find the x-intercepts, we have to figure out what goes in to make what comes out equal to 0. In other words, we have to solve the function equal to 0. So we have to solve negative 2 times x plus 3 times x minus 1 squared is equal to 0. Which looks intimidating unless you remember that being factored and equal to 0 is a desirable position to be in because of the zero factor property. If you're factored and equal to 0, then one of your factors must be 0. In other words, the only way a product can equal 0 is if one of its factors was 0. So, was it this factor? Was it this factor? Or was it this factor? And if you're wondering what about the square, don't worry, we'll talk about it in a moment. One of those three factors had to be 0. Now the first one clearly we can dismiss for two reasons. Number one, it says something that's simply not true. Negative 2 is not equal to 0. And secondly, there's no x to solve for. So we can ignore that one because the negative 2 by itself cannot cause the product to equal 0. But x plus 3 could equal 0, and if you solve that, you get x equals negative 3. And x minus 1 could equal 0, and if you solve that, you get x equals 1. So solving something equal to 0 is an old story. We've seen it many times. But now, in the context of x-intercepts of polynomial functions graphs, we need to dig a little bit deeper. To find the multiplicity of an intercept, you simply have to look on the power that was on the factor that gave you the intercept. In other words, this negative 3 came from this factor. What power was on it? Well, it's not written, but it's an implied 1, which means the multiplicity of this x-intercept is 1. I'm just going to write mult for short. What's the multiplicity of this x-intercept? Well, it came from this factor, and the power on the factor was 2. So the multiplicity here was 2. So again, the multiplicity is simply the power that was on the factor that gave you this x-intercept. Let's go ahead and find all the zeros and their multiplicities, and then we'll talk about crossing the x-axis versus touching and turning. Now sometimes the x-intercepts are easy to spot, sometimes you have to work a little bit harder. For example, on part B, we have to solve this equal to 0. 5 times x squared minus 4 times x plus 1 squared is equal to 0. And that will only happen if one of the factors is 0. Now speaking of factors, one of these factors can factor further. Do you see which one it is? X squared minus 4. X squared minus 4 is a difference of squares, and so we can factor it by unsquaring the x squared to get x and x, and unsquaring the 4 to get 2 and 2. One gets a plus, one gets a minus. Foil these out if you don't believe me, you'll get x squared minus 4. But now that it's completely factored, I can dig out the x-intercepts rather easily. This 5 won't give me 1, just like the negative 2 didn't. If I put x plus 2 equal to 0 and solve it, I get x equals negative 2. If I put x minus 2 equal to 0 and solve it, I get x equals positive 2. And if I put x plus 1 equal to 0 and solve it, I get minus 1. Now, if you're asking yourself right now, how come you wrote negative 2 when it said positive 2? That means that you don't need to skip this step. But if you do it enough, you start recognizing what's happening. As I solve, the number moves to the other side and its sign changes. Ideally, I would like for everybody to be able to look at this and go, I know what my x-intercepts are, it's just the opposite of the number in there. But what about the multiplicities? The multiplicity is the power on the factor that produced each of these x-intercepts. The negative 2 came from this factor, and its power is 1, as did this one, whose power is 1. But this x-intercept came from this factor, and its power was 2. One thing you can say about multiplicities is that their sum will match the degree of the polynomial. Let me partition this. All right, what about this one? No further factoring is required, although we do have an x squared, it's just a single term, not inside of a binomial like this one. So we can go ahead and solve this by putting each factor equal to 0 and solving. Or go ahead and find the x-intercepts, I should say. If we put x plus 5 equal to 0, we get negative 5. If we put x minus 4 equals to 0, we get x equals 4. But what about this guy? If you're not sure, actually write it out and go through the motions. I need to solve negative x squared is equal to 0. Well, first off, that's like negative 1 times, so you could divide by negative 1 to get rid of the negative. X squared is equal to 0. And then you could drop a square root, which normally invokes a plus minus, but 0 is the only number that's the same as its negative. So saying plus minus 0 is redundant. So here's a little something that you'll pick up on eventually. If your factor is a monomial, mono meaning one term, and it contains an x, then the x-intercept is 0. This was a monomial, but it didn't contain an x, as was that one. But again, if one of your factors is a monomial, a single term, that contains an x, then it will always solve to give x equals 0. Let me bring down these other x-intercepts. And what are their multiplicities? Well, the 0 came from this factor whose power was even, or excuse me, whose power was 2. So the multiplicity of that x-intercept is 2. Each of these came from factors whose implied power was 1. So each of these multiplicities is 1. So multiplicity is an easy question to answer if you know where to look. You just look on the power that gave you that x-intercept. But what does multiplicity give us? Well, if the multiplicity is odd, the graph will cross the x-axis, go from one side to the other. But if the multiplicity is even, then it will touch the x-axis and turn around. So to describe what I call the x-intercept behavior, does it cross or does it touch and turn, we simply have to look at the multiplicities. Any multiplicity that's odd means that you actually cross the x-axis. So this multiplicity is odd, so this graph would cross the x-axis at x equals -3. This one would cross the x-axis at x equals -2. It would also cross the x-axis at x equals 2 because all of these multiplicities are odd, as are these two. So cross and cross. So in all these graphs, at these x-intercepts, the graph would cross either from top to bottom or bottom to top, depending upon where it's coming from. But if the multiplicity is even, then the graph will not cross the x-axis, it will touch it and turn around. Think about a parabola barely touching the x-axis. So when the multiplicity is even, we can say touch and turn. Touch and turn. Touch and turn. Touch and turn. So locating x-intercepts and multiplicities are pretty easy if your function is factored, foreshadowing. But knowing how to interpret the multiplicities is also pretty easy. You just got to remember that odd crosses, even touches and turns. Unfortunately, I don't have a verbal gimmick for connecting odd with cross and even with touch and turn, but if you can come up with one, I would appreciate it. All right, and if you're wondering why don't I draw the graph, don't worry. In my master plan of things to do, all this information for each function is going to come together and make a graph. It's just that when we get to the graphing problems, I don't want to have to redo all of this, so I'll just put it on the board and we'll take it from there. So this is how you find x-intercepts, multiplicities, and x-intercept behavior if the function is already factored for you, which begs the question, what if it's not?